Good afternoon, folks, and welcome to the SAICI Geotechnical Division's first evening lecture for 2024. Just a couple of things to note for the lecture. Teams webinar creates an attendance register at the end of the meeting, which will be used for CPD purposes. Hence, there's no need to leave your details in the comments section. This lecture is being recorded. If you choose to stay online for the lecture, your consent to the lecture being recorded is implied. For the Q&A portion, please click on the Q&A icon and post your questions there for the presenters. So without further delay, let's get started with this afternoon's evening lecture. The 2023 J.E. Jennings Award recipients, Dr. Luis Alberto Torres-Cruz and Professor Dobroslov Znidarcic, will be presenting their work titled Geotechnics of Mine Tailings, a State-of-the-Art Report. The J.E. Jennings Award is made annually by the Geotechnical Division to honor the late Prof. J.E. Jennings and the outstanding role played by him in the development of geotechnical engineering in South Africa. The award is presented to a member of the Geotechnical Division who is the author of a meritorious publication relevant to geotechnical engineering in South Africa, published during the previous year, either in South Africa or elsewhere. Just by means of introduction, Dr. Luis Alberto Torres-Cruz is a senior lecturer at Wits University, where his teaching contributions include tailings management and critical state soil mechanics. He holds a PhD in geotechnical engineering from Wits. The main driver of his research has been the prevention of catastrophic failures of tailings dams. Luis's achievements include an honorable mention for the R.M. Quigley Award from the Canadian Geotechnical Journal, 2 times winner of the SAICI Geotechnical Jennings Award, and co-author of a 2022 state-of-the-art paper on the geotechnics of tailings dams. Luis's research efforts have benefited from collaborations with other academics, as well as interactions with industry. He is a chartered engineer with the Engineering Council of the UK and is a member of the British and South African Institutes of Civil Engineering. Professor Dobroslov Znidarcic is a Professor Emeritus on Geotechnical and Geoenvironmental Engineering at the University of Colorado, Boulder. He obtained bachelor's and master's degrees from the University of Zagreb in Croatia and a PhD from the University of Colorado, Boulder. His research interests include flow processes in soils, seepage, consolidation, desiccation, unsaturated soils, multi-phase flow, dams, laboratory testing, centrifuge testing, numerical modeling, field monitoring, and instrumentation. Dobroslov has received multiple honors and distinctions, including 2 outstanding paper awards from the ASCE Geotechnical Division, Special Service Award from the ASDM Committee D18, and was a Fulbright Scholar from 2001 to 2002. He is a member of the ASCE, ICOLD, and the Croatian Society for Soil Mechanics and Geotechnical Engineering. Quite a mouthful. Luis Dobroslov, over to you. You can take over the screen and share your presentation.
Thank you, Ms. Sain. You should all be seeing my slide in full screen mode. If you don't, please shout. And you should, thank you. And you should also be able to see my pointer right now. So thank you again for that introduction. And the title of the presentation today is Geotechnics of Mine Tailings, a state-of-the-art report. And as Masain has already indicated, it will be myself and Professor Znidarcic delivering the presentation. This presentation is based on the paper that was distinguished by SAICI last year. The paper, is based on the paper, that was distinguished by SAICI last year. The title of the paper is Geotechnics of Mine Tailings, a 2022 state-of-the-art. And it was one of a number of state-of-the-art reports that were presented at the International Conference of Soil Mechanics and Geotechnical Engineering that took place in Sydney 2022, and which is available for free download from the link that you see on this slide, or you can just Google the title, of course. This paper was written by a team of 5 authors. So the lead authors were Professor Andy Faree from the University of Western Australia, and Dr. Ramon Verdugo from CMGI in Chile. Then we also had contributions from Ms. Annika Belkovic from TCS in Sweden. And by the way, Annika, I see that you're in the audience today, so hello there. And then Dobroslov and myself being the fourth and fifth authors. The paper is quite comprehensive in nature, and it is divided into 13 sections. And I'm just going to briefly provide the title of these sections so that you have an idea of what type of information is contained in the paper. So there's an introduction. Then in the section number 2, we point out differences between water dams and TSFs. Then we move on to the application of geotechnical principles and discuss how tailings differ from natural soils. In the 4th section, we're looking into laboratory characterization. Section 5 deals with field testing. 6, modes of failure. 7, field behavior and associated modeling. 8, methods of analysis. Number 9, monitoring. 10, governance. 11, closure and residual liabilities. And the paper finishes with sections on discussion and concluding comments. Now, of course, today's presentation, the time allocated to it, would be not nearly enough to go through all of these sections. So Dobroslav and I will be presenting mostly on the topics that we contributed to the paper. And the presentation is then divided in 2 parts. Firstly, I will present on CSL testing, difficulties with CPT interpretation, and lessons from failures. And then I will hand over to Dobroslav, and he will be presenting on sedimentation, consolidation, desiccation, creep, and filling analysis and seepage. Okay, so let's get started with part 1. And I will begin by talking about the critical state line or steady state line, as some of you might know it. Most of you will be aware of the fact that a critical state line is essentially defined in 3-dimensional space, and we typically use 2 projections to capture that 3-dimensional nature of the critical state line. One of the projections is void ratio versus mean effective stress, and the critical state line is defined by these points, where each of these points defines the critical state that was reached in a triaxial test. So it is quite an endeavor to get a critical state line, because for each point that you want to use your critical state line, you have to run 1 triaxial test. Now, as with any straight line, you're going to need 1 slope and 1 y-intercept to define that straight line, to come up with a mathematical formulation for it. That slope is what we generally call lambda, and the value of lambda is going to depend on the value of the logarithm that you are using for the mean effective stress. So in this case, I have a log 10, therefore we call that lambda 10. But if you change the base, then the lambda changes accordingly with an equation that I'm going to show you just now. And then as for the y-intercept, well, as you can see here, the mean effective stress is on a logarithmic scale. So you don't really have a y-intercept, because you don't, on a logarithmic scale, you cannot have an x equal to 0 value. So the most common practice is to adopt the x value when p prime is equal to 1, and that is called gamma 1. But you don't have to choose 1. You can choose any value. You could, for instance, choose gamma 100. And that gamma 100 would be the value of the critical state line when P prime is equal to 100 kilopascals. Can you still hear me? I think my pointer has frozen.
Yes, we can still hear you. Yeah.
Okay, thank you. Let me just plug in a cable here just to make sure. Okay, so oh, just a minute. Just a minute. Okay, PowerPoint is not responding. Just 1 second. Apologies for that. Apologies for that. Okay, you should be able to see my presentation again. Okay.
All good.
All right, thank you, Maseng. There's the equation. If you ever have to deal with data, calculated lambda values calculated using 2 different logarithmic bases, well, now you know how to switch from one to the other. And let me touch now on the importance of this critical state line. Why is it that we pay attention to it when dealing with tailings? Well, essentially, your critical state line or steady state line divides this space of void ratio versus mean effective stress into a contractive area and a dilative area. Now, I want you to think what happens if you have a point here in the dilative area and you shear this specimen undrained. Now, by definition, because of how we have defined this critical state line, we know that this specimen is going to want to move towards its critical state line. And in this case, when it's on the dilative side, it would move towards the right. It can only move towards the right and not up and down because we're saying here that this is an undrained shearing, therefore the void ratio cannot change. And if it moves towards the right, it implies an increase in mean effective stress, which in turn results in an increase in shear strength. So that's all good. The opposite happens if you're on the contractive side. If you're over here on the contractive side and you have undrained shearing, then the only way the specimen can approach its critical state line is by moving to the left. And that implies a reduction in mean effective stress and therefore a reduction in shear strength, which is not good. I said that the critical state line exists in a 3-dimensional space. Now, the void ratio versus P prime space that I was showing in the previous slide is one of the 2 projections that we can use to capture that 3-dimensional nature of the critical state line. The other projection is this stress space right here, which is defined as Q versus P prime, essentially deviator stress versus P prime. Now, in this space, the critical state line is always straight and it always passes through the origin. In other words, the y-intercept is 0. If the y-intercept is 0, then you only need a slope to define this projection of the critical state line. And this slope, which in this case is 1.25, is what we call MTC, where TC indicates that it has been obtained from triaxial compression testing. So this M is generally termed the critical friction ratio. So in summary, we need 3 parameters to define the critical state line. That would be your gamma, your lambda, and this slope m. Now, let me say one more word about this QP prime projection. I really like this projection because it is independent of the particle size distribution of the soil that you are analyzing. At least this is the case for non-plastic tailings. And we have seen this in several data sets that have been reported in the literature. So for example, here we see it for fluoride tailings. And regardless of the particle size distribution that is being investigated, they all fall on pretty much the same line in this Q versus P prime space. And over here, we see it with platinum tailings. Again, 3 different particle size distributions, but they all are defining essentially the same critical state line, the same value of MTC. A couple of years ago, there was a round-robin paper that was initiated by colleagues at the University of Western Australia. And it was a round-robin for critical state line testing, where essentially what they did is that they sent the same tailings, the same particle size distribution of tailings, to a number of laboratories around the world. You see them listed over here. It's to the tune of 12 or 15 laboratories. And they requested these laboratories to calculate the critical state line of the tailings. And when the results came in, this is what they found. What they see is that in void ratio versus P prime space, there is significant scatter in the data. Okay, you can see that the points are not really defining a line anymore, but more like a swath or band. Whereas in this stress space of deviator stress versus mean effective stress, when you consider the same data from the same laboratories, you do see a reasonably well-defined critical state line. So I think that this comparison of results holds a critical answer, a critical consideration as to what makes the calculation of a critical state line difficult from a practical point of view. So why do we have more scatter over here on the left than on the right? Now, I will point out to you that the determination of this projection requires only the calculation of stresses, whereas the determination of this projection over here requires the calculations of a void ratio. So what this comparison suggests to me is that the key to an accurate calculation of the critical state line is in making good calculations of the void ratio. So with that in mind, I want to share with you some recommendations to achieve a well-defined critical state line. Recommendation number 1 would be to use contractive specimens because dilatant specimens are prone to strain localization. And this was very nicely demonstrated in this paper from 1996, in which they used microcomputed tomography to track the distribution of void ratios inside contractive and dilative specimens. So always go for contractive specimens. Recommendation number 2, the data suggests that the critical state line is independent of the sample preparation method. Therefore, we should be trying to use the method that best controls the void ratio that you're going to reach when you are preparing the specimen, and that method is moist tamping. Right, so to implement moist tamping, you maybe have to do a bit of an effort at the beginning to create the tools that will allow you to implement moist tamping robustly. But what I have found is that it does pay off. The catch here is that, notice, this is the preparation void ratio. In other words, you are controlling the void ratio. You have really good control of the void ratio as your specimen exists like this, as I'm showing it on the right-hand side. After you do that, you still have to saturate the specimen and you still have to consolidate it. And that is going to induce further changes in the void ratio that you cannot control. But I say, hey, well, best to have some control than no control at all. I should also point out that the round robin paper that I was making reference to earlier shows that under compaction and the number of layers that you use to build your triaxial testing specimens do not affect the resulting critical state line. Recommendation number 3, well, generally, undrained tests are useful to define the critical state line at low values of P prime, whereas drained tests help define the critical state line at large values of P prime. And that's illustrated over here, where your undrained tests, and we know they are undrained because the state path is horizontal, they are defining fairly low values of P prime, but this drained test over here is defining a higher value of P prime, in this case, close to about 700 kilopascals. Now, an advantage of running a drained test is that if you have an estimate of MTC, and you may have that estimate from testing different gradations or from your undrained tests, then it is possible to estimate the P prime value that a specimen will reach at critical state. So in other words, if I go back one slide, and let's say in this case, if I already have 4 points on my critical state line, I may be wanting to better define my critical state line over here. Say I want a point between this one and this one. In other words, I want a point at a critical state P prime value of, this is 200, 300, of 400, right? Then if I want the critical state to be at 400 kilopascals of P prime, then I can plug in those 400 kilopascals in this equation over here, and this is going to give me P prime I, which is the consolidation level at which I need to set that triaxial test. And then number 4 is that void ratio determinations require the measurement of the water content at the end of the test. There is no way that you're going to get reliable void ratios if you are basing them on measuring the dimensions of the triaxial testing specimen. And these reliable measurements of the water content at the end of the test have to be done either by the freezing method or the squeezing method. So for details of the freezing method, you can have a look at this reference right here. And for details of the squeezing method, you can have a look at these 2 references right here. In the 2022 CSL round robin paper, we find this statement that the laboratories that used the freezing method produced the most consistent CSL definitions. And there seems to be the idea that the freezing method leads to more reliable void ratio measurements. And that's a bit problematic because not all soil laboratories are fine with the freezing method. Some of them don't like the idea of putting their triaxial cells in the freezer because, or the base of their triaxial cells, at least in the freezer, because it might damage some of the components of the base. And I would say that there is no reason, or I know of no reason, to why one should not use the squeezing method. Okay, the first advantage is that the laboratories will not object to it, but perhaps more important than that, this critical state line right here comes from this paper from 1996, and it is one of the best defined critical state lines that I have seen in the literature. It is really well defined. The scatter is very low, and it was determined using the squeezing method. And then the last thing that I would encourage you to keep in mind is that not all critical state lines are equally reliable. So whenever you get a critical state line, make sure that you're not getting only the line itself. In other words, not just the gamma and the lambda, but that you also have a look at the amount of scatter in the underlying points that are defining that critical state line. So this is quite intuitive, right? If you have a great degree of scatter, then you're going to have less trust on that result than if you have a lower degree of scatter. Now, I want to move on to CPT interpretation, and in particular to difficulties regarding CPT interpretation. Now, I focus here on the CPT because it seems that in today's geotechnical practice in tailings, CPT is the preferred tool to assess the mechanical competence of tailings. And this is reflected to some extent in the reports that have investigated the failures of several high-profile dams over the last decade or so. So here I have the report for the Fundão tailings dam failure, here the one for Cadia, and here the two for Brumadinho, one that was led by Robertson and the other one by the colleagues in the University of Catalunya. And I am highlighting the methods that focus on the estimation of the state parameter. I suspect most of you will be familiar with the concept of the state parameter. I showed it a few slides ago. Is that vertical offset, that void ratio offset between a specimen and its critical state line. So you can see that there's been a strong emphasis on calculating the state parameter in these reports. We clearly have a lot riding on this idea of calculating the state parameter. You can see that for the Simne report for Brumadinho, that's what they were looking at. Here for the Brumadinho report led by Robertson, it was the preferred approach, and the same over here for Cadia, it was the preferred approach. So I think it is critical that we ask ourselves, is it really possible to infer the state parameter of loose tailings deposits? Now, the method that seems to have emerged as the best way, as the most rigorous way of inferring the state parameter is what has come to be known as the widget method that has been developed by Shuttle, Jeffries, partly by Bean as well, and their collaborators. And it appears that when one is trying to answer this question, is it actually possible to infer the state parameter of tailings using the widget method? Often one ends up facing this figure right here, which comes from a 2008 paper by Gafgassi and Shuttle, which shows you the state parameter that was actually measured versus the state parameter that was calculated using the widget method. And now at first glance, this figure seems quite convincing, quite compelling, right? Here you have all of the data plotting around the identity line, the x equal y line. However, there's a number of considerations that we must keep in mind when assessing the weight, the validity of this data as a means of validating the result of the widget method. The first thing is that the data that you see here was fitted, not predicted. In other words, there was no distinction between training data and testing data. The second thing is that this considered only CPTs, and as I will show you just now only drained CPTs, and as I will show you just now, in tailings, we don't always have drained CPTs. The third point is that we have to notice the dominance of dense soils. In other words, the dominance of soils that have negative state parameters, whereas what we're actually interested in is loose tailings deposits that have positive state parameters. And the fourth point is that the data come from calibration chambers and not an actual tailings deposit. So let's have a closer look at some of these. Here we can see how this is CPT data from Marisbreit, which you probably know failed back in 1994 right here in South Africa. And you can see that very often in tailings dams, you will have some CPT data that is drained, but you can also have data that is partially drained or even undrained, at least according to this chart. Secondly, I pointed out at the fact that data was obtained in calibration chambers. Now, there are big differences between a calibration chamber and an actual tailings deposit. For starters, in a calibration chamber, the horizontal stress is known, or at least you can make a very reasonable estimate of it. But in the field, this horizontal stress has been referred to as the black hole of geotechnical engineering. And this comes from a reference from 1992, and you might think, well, that was 22 years ago. Surely things have changed now. But if you look at the post-failure reports for Fundão, Cadia, and Brumadinho, you will see that the horizontal stress ratio has been assumed in all of them rather than measured. So it seems that not much has changed in terms of measuring the horizontal stress ratio. Another important consideration, another important difference between calibration chamber and an actual tailings deposit is that in a tailings deposit, you can encounter very fine layering. And when I say very fine, we are talking about centimeters and sometimes even millimeters, as you see here. And you can encounter this in gold tailings, in iron tailings, in all sorts of tailings. And this means that the particle size distribution is changing from one layer to the next. And that leaves us wondering, well, if there's a change in particle size distribution, then there will be a change in the critical state line. So which is the critical state line of this? I have not seen investigations into it. I believe at this point, the short answer is we don't know. But perhaps the most important thing is that whenever we are assessing the value, the validity of an engineering methodology, it really, at the end of the day, the ultimate test of that methodology is not the assumptions or where it was published or who published it or how fancy the mathematics is. It doesn't matter. Only one thing matters. And that thing that matters is if your predictions are matching the measurement. That's it. Of course, I'm talking from a practical point of view. From a research point of view, we can argue about that. But from a practical point of view, is do your predictions match your measurements? So to test the widget method, we would need to check what are the predictions that were made in an actual tailings deposit, okay, not in a calibration chamber, in an actual tailings deposit, versus what was the state parameter that was measured in that tailings deposit. And that's the data that we have compiled in this figure using three different sources. And we can see that there is, in general, an unconservative bias in the estimates made from the widget. Now, you might say that for this 2019 reference, the data seems to be in line, well, or plot close to the identity line. However, it seems to me that this should be interpreted as, okay, the widget method looks promising, but that in general, this figure is a reminder that the validation of the widget method in real silt deposits is a pending task for the geotechnical community. In other words, we don't know if it works yet. And coming to my last slide, it's really just a quick excerpt from our paper that was included in this section, which is called Reconciling the Results of the Expert Panel Report and the SEMNE Report on the Causes for the Brumadinho Failure. These two reports, these were two independent reports that looked into the Brumadinho failure, and they arrived at different conclusions about what had caused the failure. We comment, a rational approach to the dilemma resulting from the different conclusions that these two reports arrived at is perhaps to adopt the approach suggested some time ago in previous works, which is, if there are tailings that are liquefiable, assume they will liquefy, rather than trying to predict plausible trigger mechanisms. Simply assume liquefaction will be triggered. Although this is certainly a seemingly logical suggestion, we do acknowledge that it comes at a sometimes substantial financial cost. In other words, it's expensive to be building all those buttresses. Now, I suspect that this is a position that maybe not everyone will agree with, but I'm sharing it here just to share what was our position in this regard in the paper. And with that, I'm going to stop sharing so that I can hand over to Dobroslov.
Thank you, Louis. Do you hear me?
I can hear you loud and clear.
Okay, then I can share this. Let me get into my presentation mode. Do you see my pointer and my part two here?
Yes, Dobroslov. Yeah.
Yes. Okay. Thank you.
Yeah.
So, well, I'll show some of the stuff that I have contributed to this paper. First of all, on the question of how do tailings refer to the typical soil mechanics problems or typical soil mechanics issues? It's that we have, just a second, I need to change my presentation here. Okay, here. Indeed, tailings are very soft soil that are undergoing sedimentation, consolidation, desiccation, and creep upon deposition. So let me just highlight some of these processes. First of all, here we have a graph that shows the relationship between the void ratio of a kaolinite clay, pure kaolinite clay, mixed at the initial void ratio with certain amount of water, and then measuring the void ratio that corresponds to the zero effective stress. So that would be this, if you have a suspension of that kaolinite and you let it sit in a jar until it settles completely, you will see that at the very top, where the effective stress are clearly zero, you have the void ratio that is initially equal to the initial void ratio until you reach the initial void ratio of about 8, at which point the void ratios beyond this point at zero effective stress are getting a little bit lower than the initial value. This is what Ray Kryzak defined as a fluid limit in continuity from the plastic limit, liquid limit, and fluid limit. In other words, limit at which the soil is established as a soil, meaning that the effective stress principle is applied. So if we deposit the material at the lower initial void ratio, it may not undergo sedimentation, but if it is deposited at the higher void ratio, it will first undergo sedimentation until it reaches the consistency that corresponds to the soil. So that is the this part on this. Because these materials are so soft, they require some special testing. Our conventional consolidation tests will not work necessarily well for these materials. So we have developed the laboratory procedures that allow us to determine consolidation properties and use it in predicting the consolidation behavior in the field as well as desiccation. The testing procedure is based on a seepage-induced consolidation test that was originally developed or proposed by IMAI, but this test was somewhat modified in the analysis part of it, where we solved the inverse problem solution to obtain the parameters. We characterized the void ratio effective stress relationship in the form of a power function that is was originally proposed by Somogyi, but we added another parameter Z to identify the initial void ratio for that material, and that void ratio for sigma dash equals 0 would correspond to our zero effective stress void ratio. We can obtain, therefore, in a single test, we can obtain the relationship between the void ratio and the logarithm effective stress. And we will find that many tailings will be either coarse grain materials, which relatively low void ratios, or fine grain materials, which will have high void ratios. We obtained from this test not only the void ratio effective stress relationship, but also the hydraulic conductivity void ratio relationship that will be presented in the original form that Somogyi proposed somewhere in early 80s. And you will see here that the void ratio hydraulic conductivity relationship are actually, again, for fine grain soils, will cover lower range of the void ratios, but for coarse grain soils, but for fine grain soils, it will cover a wide range of the void ratio changes, as well as several orders of magnitude change in hydraulic conductivity. So the first thing that is important to recognize that indeed these are materials exhibiting very nonlinear relationship in both compressibility and hydraulic conductivity, and therefore taking some average values is never going to correctly represent the behavior of these materials in the field. So first step in characterizing our tailings is basically to obtain these properties so that we can predict their behavior in the field. In order to, we have also found out that many of these tailings will undergo consolidation and desiccation following the assumptions and following the procedures that were originally proposed in 1967 by Gibson and his core workers. However, if we treat these tailings with some chemicals, some flocculants, we create flocculated structures in which you have the material full of flocks, various size flocks, but the flocks that are not rigid. They are deformable, and therefore they will, as the stress is applied to them, they will slowly deform not only in volume, but in shape as well. And that will lead to non-unique relationship between the void ratio and the effective stress. We found out, we started developing this technique for oil sands tailings in Canada, and we found out that for these materials, the compressibility or the volume changes not only as a consequence of expulsion of water under the effective stresses, but also as a consequence of elapsed time. And so in that case, we will have different compressibility curves for different duration of tests or different duration of loading. So we have decided to model this with the same type of curve, the same relationship for compressibility, but now each of the three parameters in that representation, A, B, and Z, will be the function of time as well. And so you have here time in all of these parameters. Now that may look very complicated, but it's actually really two parameters that are important. These are the parameters parameters 1 and 2, A1 and A2, B1 and B2, Z1 and Z2, because the other parameters, A final, is the value that we anticipate to be the ultimate compressibility curve after infinite time, which obviously we will never be able to measure it, but we can extrapolate to that value. And A0 is the initial compressibility curve corresponding to 0 time, and so on. And you can see here from some experimental data that we can measure these curves at different times, at typically up to a month, I would say. Running any test longer than a month is pretty tricky. But after measuring these changes in the compressibility curve for a period of a month, we can find the values of different A, B, and Z values, and then interpolate the function that looks like this and characterize this material for creep or time-dependent compressibility of the material. Okay. So now, when we have the material characteristic that we can use, we will demonstrate the process of consolidation, desiccation, and creep on a very simple example where we have a column of these tailings that is 5 meters high, and we will predict how this material will behave with time. Here you have the settlement curve for this material, and you will see we represent both the coarse and fine tailings. In principles, they are exactly or very similar curves, except that the rate of change is different. Of course, for fine tailings can take a very long time. And here you can see where is the problem, is that very often, even for such a simple column, fine tailings, typical fine tailings that you will find, they may require several years to consolidate completely. For coarse tailings, that may be a matter of weeks or months and so on, but for fine tailings, it's a very long time. Here we are predicting or showing the change in the void ratio versus time during the consolidation process. On the left-hand side are basically is for coarse grain material. On the right side is for fine grain material, and they are in principle very similar, except the magnitudes of the void ratio change are different. But if you look at this fine grain material, you will notice that the initial void ratio, if the material is dumped in this column instantly, the initial void ratio would be constant with depth of about 12.5, 13 or so. And then the consolidation, even though this was undrained column at the bottom, the consolidation will start actually from the bottom. The initial excess pore water pressure will create an upward gradient that is initially exactly equal to the critical gradient for that material, which will maintain the void ratio constant in most of the column. In other words, the critical gradient is keeping it buoyant until the consolidation front reaches the top, when you start getting the concave form of the curve to the final value. So this is just for consolidation mode. After the consolidation is completed, or during the consolidation, we can also have desiccation or shrinking of that material, because we have evaporation or we have a drainage to the bottom and so on, and we wanted to model this desiccation as well. And so here, if you look at this, to understand this, it's important to look at this what we call shrinkage curve, basically, which gives you the water content, initial water content at which the slurry is mentioned, and the void ratio is here. Of course, when the material is saturated, then the void ratio is directly calculated from water content by multiplying it with specific gravity. Okay, and then you will see that in shrinking material, you will have a saturated condition all the way until you exceed air entry value into this material, which in many cases will be, especially for fine grain material, will be very close to the shrinkage limit. So this would be shrinkage limit. Material is not going to reduce in void ratio below this value in the drying process. So this would be the shrinkage limit. Then if you have air entry value that is reached before the shrinkage limit, then this curve will start deviating from here and may go like this to the end of this. So just to understand what the shrinkage process looks like. Here is an example for desiccation modeling for the same materials that we did for the consolidation modeling for the same column of 5 meters with an effective evaporation rate of 3 millimeters per day. And we can see here now initially the consolidation will produce settlement rate that are higher than 3 millimeters per day, and therefore there will be no evaporation. But once the settlement rate drops below that value, then the desiccation overcomes, and this obviously will produce 3 meters of settlement due to desiccation in 1,000 days here for the fine materials. You will see the desiccation here will also start creating a crust on top of this material, where we will have crusting while the consolidation is still undergoing underneath. We will develop crust. Depending on the ratio of the void ratio versus of the hydraulic conductivity of the material versus the evaporation rate, this crust may be very deep and slowly developing, or it can be very, very shallow, very, very thin and developing very fast. If we had, let's say, 5 times higher evaporation rate, this crust would start developing much earlier and it would go much faster and would create a very, very dry topsoil. And the desiccation will progress until you reach the shrinkage limit of this material, or either in the whole layer or at the very surface. Once you reach the shrinkage limit, the material will start desaturating, reducing hydraulic conductivity further, and therefore preventing effective evaporation. That's why the desiccation practically stops at the moment when you reach the shrinkage limit. We have done some work in Florida and basically monitored for about 1.5 years, monitored phosphatic clay that was settling, and we were able also to predict the development of the cracks with this part here. So we had a prediction that the crack would start developing after about almost 1 year of our observation, and then we measured these cracks developed in there. And you can see now here that the cracks stopped growing because there was basically the desiccation process was terminated. We can get desiccation also not only due to evaporation, but also due to the drainage to the bottom. In that case, we don't even need any evaporation, but if the water is coming down after consolidation, you will start getting lowering of the groundwater table, okay, until the water table reaches the bottom of the drained under drain, assuming that the under drain is draining into the atmospheric pressure, and you may end up with the material that has a uniform void, more or less uniform void ratio, or even going to the left of here due to hydrostatic capillary force above the water table. So we can model this part as well very efficiently with this approach. We will now show the same column of the 5 meters high over with the creep characteristic that we obtained to a bentonite slurry. In this case, you will see that the consolidation only would produce the final settlement of about 3 meters. But please note for this material what is the time scale. We are talking about hundreds of years of consolidation in such a active and low pervious material. If we add creep will produce an additional settlement of 1 meter, but note also that up to about 60 years or so, we will have no difference in the behavior of these two materials. So of these two examples. Here is the, again, void ratio profile with height for the consolidation only, as you can see, again, for these years. But if you include creep, then you will notice that even during the consolidation portion, for example, after 303 years here, you will have practically finished consolidation, okay? And your bottom void ratio is about 12. But at the same time, if you have creep, that bottom void ratio will be below 10. It will be somewhere around 8 or so. And therefore, indeed, creep is taking place during consolidation. And we can predict what this effect is going to be. Of course, when we are talking about flocculated structure, that usually increases the hydraulic conductivity of the material, and as such, the consolidation process is very fast, and therefore creep is the dominant process in that analysis. Now, these models that we have developed and that we use in consolidation analysis are basically one-dimensional models. It's basically just a column, which obviously is correct. For tailings facilities, we obviously have three-dimensional problem. However, we should recognize that in these cases, usually the heights we are talking about maybe a couple hundred meters height, but extent of several kilometers, or at least a kilometer or so. So in other words, even in that three-dimensional case, the dominant seepage problem, or this dominant consolidation, will be dominated by the behavior of the material in the vertical direction. The horizontal seepage, the radial seepage will not have a significant effect on the rate of consolidation. However, because the facilities are three-dimensional, we do need to address this three-dimensionality, and we have therefore developed a procedure where we take an elevation area curve for the storage facility and discretize it into several layers. Now, if we do that, we have two choices. Either we can analyze this storage capacity as horizontal layers and try to see how this will be filled by changing the filling rate for each one of these layers, or we can divide it into columns, as I will show in the next part. Let me mention that this horizontal discretization will produce the filling rates different for each height, but in reality we are analyzing only the central column here. We are not accounting for the fact that the other columns, the other parts of the impoundments are shallower. And therefore, we are basically assuming that the material on the sides of the impoundments is also compressing at the same rate as the tailings itself, which obviously is unrealistic assumption. Otherwise, we can divide this, discretize this into columns, and then we start filling each column. Now, this requires multiple analysis, where we fill first column to the bottom of the first adjacent column. Then we start filling this column here to the next one, and then while we are filling this part here, we are basically allowing this to settle, and therefore we have to come back here and refill this one column to get to the same level. And so by doing this repeated analysis, we maintain constant level of this tailings in all the columns, but recognize the different heights of different columns. If we do that analysis, then we call this 3D method, while the previous one was the 1D method. And so you will see that the filling may look something like this. And you will see now that the 1D method will produce much larger prediction capacity for the tailings, or much longer life of the column, because we overestimate the volume available on. Well, in this situation, we actually slightly underestimate this volume. So basically, we call this lower bound. This is an upper bound. Both of these curves show dramatic change in slope here. Why? Because for that particular example, the top layer was so wide that the filling rate became so slow that the consolidation process caught up with the filling process, so to speak. We developed what we call Filcon model, and this one will give you basically several curves. It will give you the first curve that if you were basically filling your impoundments with water, with non-compressible material, okay, then it will be filled in, let's say, 2,000 days. If you recognize that there is a sedimentation going on, which is usually a very fast process, then, and you are therefore filling it at the void ratio that is equal to the zero effective stress void ratio, then this may be filled in about 3,000 days, let's say, this particular impoundment. If you are filling it so slow that you are basically allowing the material to consolidate completely at every moment, then you can see that this facility would have a very long time, and it would basically accept a lot of material. A real filling rate that you may have will, let's say, fill this facility in 4,000 days, but then it will continue settling until it reaches the final state. So these are the tools that we have developed that allow us to predict the behavior of tailings upon deposition. I want to emphasize the importance of the seepage modeling. And if you realize that we realize that seepage modeling is unfortunately not always done in light of the stability of the structure. It is mostly performed to calculate water balance for these structures. But we are here focusing on the stability of the structures. No matter how you build a dam, this is an example of an upstream construction dam. Obviously, you will want to have this material to be less saturated. You will want it to be dry or unsaturated completely. But eventually, in the tailings facility, you will have a settling pond. You will have saturated material. Now, as I mentioned earlier, the hydraulic conductivity of these tailings reduced dramatically with the increase in effective stress and decrease in the void ratio. Therefore, in any facility, you will have lower hydraulic conductivity at the bottom, which will prevent the seepage or this water to drain to the bottom. Maybe it will drain somewhat, but it will definitely be impeded. Okay. On top of that, we may end up having anisotropic materials, as Lewis showed that they are indeed layered, which will create higher hydraulic conductivity in horizontal direction. And therefore, we can expect that this water, the only place where it could seep is towards the downstream slope. Okay. On top of that, this portion of the material is initially unsaturated or have a lower saturation than the rest of the material. Therefore, it will also have a lower hydraulic conductivity, which will mean that it will force the higher pore pressures to develop here. So the person who addressed this issue was Blight in 1994 in his book, where he showed the difference between the phreatic surface for isotropic and constant permeability, And then he assumed that the hydraulic conductivity is actually being increased downwards. And if it is increased downwards, it will lower the phreatic line down and therefore make the structure more stable. Okay. But if the hydraulic conductivity of this material is lower than the hydraulic conductivity of this material here, the opposite will be true. And therefore, this hydraulic conductivity, this phreatic line will rise. We have done some analysis on to address this unfavorable seepage condition. Reduce hydraulic conductivity depth, anisotropy with higher hydraulic conductivity in the horizontal direction, unsaturated tailings with lower hydraulic conductivity near the downstream slope. All of these conditions will create seepage conditions with higher phreatic line and higher pore water pressure near the downstream slope, eventually leading to slope failure. We have done some, this is from some centrifuge experiments, where the saturated seepage analysis would be shown here in the blue lines, and the actual seepage analysis, because of the lower saturation of this part of the slope, it basically created higher phreatic line and higher pore pressures in this part. As you know, any seepage that is going to downstream slope of any sloping structure will definitely cause piping, will cause, and ultimately slope failure. So this summarizes what we have presented in this paper. Thank you.
Thank you, Luis and Dobroslov. Let's see if there are any questions. Please post your questions in the Q&A section or in the comment section. We'll give it a couple of minutes.
Saying, if I may ask something to Dobroslav.
Okay.
Dobroslav, I didn't quite understand, why is it that in some cases the compressibility characteristics of the tailings will become a function of time? Exactly when is it that that has to be a consideration?
Okay. Do you hear me? I guess yes.
Yes. Yeah.
Yeah. Well, as I mentioned, creep has been a hot topic in soil mechanics ever since the first international conference in 1936. So people have recognized that even after the consolidation or compression due to excess pore water pressure dissipation, the soil structure leads to additional deformation, additional settlement. Okay. We have, and you know, that has been debated for almost a century now. We didn't find that to be critical issue for tailings until we encountered tailings in oil sands industry in Canada, when they started to use polymers to flocculate the structure and increase the rate of water release initially. Okay. And these polymers create flocculated structures that create flocks of the material with large pores in between them. And so if you do the consolidation analysis of this type of material, it will actually be very quick. The water will freely flow out of that material, okay, initially. And therefore, if you do the consolidation analysis, you will say, okay, everything is done in you know, first few days in a 5-meter column. But then we notice that beyond these few days, where theoretically settlement should have stopped, the settlement continues and continues for a very long period of time. And we recognize that the nonlinear finite strength consolidation theory, as the way we have used it, together with the testing procedures that we developed, is not adequate to address this issue. So we recognize that what we are seeing here is a time-dependent compressibility of the material. In other words, these flocks, as you apply effective stress on them, start deforming laterally, start changing their shape, and produce the additional volume reduction. However, that process is viscous process. It doesn't happen instantaneously. So the moment you apply the effective stress on it, doesn't go immediately to the final void ratio, to the final volume, but rather it takes time for this to develop. So it's basically a viscous process. And we wanted to develop the tools to rationally analyze that phenomenon.
Thank you. Thank you. Yeah, that's clear.
Okay, it doesn't seem like there's any other questions. Thank you again, Luis and Dobroslov, for a very interesting presentation. Any parting shots from either of you?
Marcin, thank you and the SAICI Geotechnical Division for this opportunity. We greatly appreciate it.
Only a pleasure.
And as people digest possibly the paper that we have written or the presentation here, we are definitely will be happy to answer any question that is directed to us, in the form of email or whatever. So we'll be glad to clarify.
Thank you very much. Okay, so that brings tonight's evening lecture to an end. Thank you again to the presenters for availing yourselves to share this information with a wider geotechnical fraternity, and congratulations again on receiving that award. We still have a couple of more evening lectures planned for 2024, so please keep an eye out for the dates and times in the due announcement newsletters. Till next time, good night.